Let's do a calculation on how fast the charges move in a wire. This is called the drift velocity. We're going to have a copper wire. We'll say the length is 20 centimeters with a radius of 0.1 centimeters. And let's say it's carrying a current of half an amp. How fast are the charges moving in order to produce that current? Well, current is charge per time. The charge is going to be evenly distributed throughout all of this material. We'll assume there's 1 electron per atom of copper that's mobile. So we're going to figure out the total mobile charge that's available to move, and we're going to see how long it takes for it to move across this wire and get that time. Well, the Q mobile is going to be the charge of an electron times how many electrons we have available, and that's going to be the number of atoms in this wire. This is all going to come from the information given about copper. The mass of the wire is equal to the density times the volume. We have the density. We need to multiply by pi r squared times length. That's the volume of the cylinder. Plug in 0.1 centimeters and 20 centimeters, and we get 5.63 grams of copper. Now I want the number of atoms, but I have the mass. Well, I think I'm going to have to look at the atomic mass, 63.5 grams per mole. Well, that's going to give me moles. Throw in Avogadro's number, and we get 5.34 times 10 to the 22nd atoms. Well, if we have 1 electron per atom, we can now calculate the mobile charge. Holy cow, 8,544 coulombs? Yeah, well, there's a lot of atoms. That's a lot of electrons. Even though they're very small, each one in charge, it adds up to a lot of charge. Well, we know the current. We can get the time. I get 17,088 seconds. Well, that's the time for all of this charge to move past this point at a rate of 0.5 amps. Well, we can now take this distance, divide by the time, and see how long this takes. 20 centimeters divided by 17,000 seconds. Man, is that slow. So as we can see, the velocity of these charges is very slow. So what kind of energy do we have to be concerned with in a circuit? Kinetic or potential? Let's calculate the kinetic energy of all of those electrons. We know the mass of an electron, and we know how fast it's going on average, and we can calculate the kinetic energy of 1 electron. I get 6.2 times 10 to the minus 41 joules per electron, multiplied by the number of atoms, because that's how many electrons we have that are moving, and we get 3.3 times 10 to the minus 18 joules. Well, now we should compare that to the potential energy difference across this wire. Well, the voltage difference has to do with the potential energy, and that's equal to IR. The resistance of the wire is equal to the resistivity of this material times its length over the area. Now, we know about the length because the longer this is, the more the charges have to pass through the material, and that's going to increase the resistance. The wider it is, the more paths it has, and it's easier for the charges to flow through. So this is the same thing as talking about resistors in series versus parallel. So the cross-sectional area is 3.14 times 10 to the minus 6 meters squared. The resistivity of copper is 1.7 times 10 to the minus 8 ohm meters, which you can look that up. And the length is 0.2 meters. Putting all that in here, we get about 0.0011 ohms. We have half an amp. Well, the change in voltage across this wire to produce this current has to be 5.4 times 10 to the minus 4th volts. That means each one of these charges has to drop that much voltage. Well, that's the Q mobile times the change in voltage across the wire. Take the Q mobile, multiply by the voltage. We get 4.6 joules. Take a look at that. No contest. This is how come we only deal with voltage, which is the potential energy per charge, and we ignore the kinetic energy in a circuit.